And we're back with another build. But this time, we're not building a motor. We're building something much more important, a complete servo actuator for a robot. In my previous video, I built an axial flux motor that had the potential to be an absolute beast for this project. Unfortunately, the design really needed a steel core, and right now, I'm limited to 3D printing everything in plastic. But that's not going to stop this project. The goal is to build a fully 3D printable collaborative robot, or cobot, from scratch. Now, if you're wondering what makes a robot collaborative, it's because these robots are designed to safely work alongside humans without the need for safety fences. Industrial cobots constantly monitor the torque produced by each joint. If they detect an unexpected load, like hitting a person or an object, they can instantly stop the motor, making them much safer than traditional industrial robots. And to do that, you need high-torque servo actuators. So, let's build one. This is the finished 4-to-1 actuator, which forms the foundation of the robot's joint. Inside is a planetary gearbox that converts the high-speed, low-torque output of this 5010 brushless DC motor into a slower, much higher torque output, and that's exactly what robots need. Unlike drones, robots don't care about spinning at thousands of RPM. What they need is controlled motion with as much torque as possible. Years ago, hobby robots were almost entirely built using NEMA 17 stepper motors. They're cheap, simple, and easy to control. But if you're trying to build a robot that behaves more like an industrial arm, brushless servo motors are the future. The problem is that industrial servo actuators cost hundreds, sometimes thousands of dollars. On the other end of the spectrum, hobby servos are tiny and don't produce nearly enough torque for larger robots. So in this series, we're building our own. A completely 3D printable BLDC servo actuator that's modular, affordable, and eventually capable of 100-to-1 gear reduction. In this video, we'll build the first stage, the 4-to-1 planetary gearbox. The complete CAD files and assembly guide are linked in the description below if you'd like to build one yourself. Let's get started. Here are all the parts you'll need. First, you'll obviously need a 3D printer to print all of the components. You'll also need a basic screwdriver set, and I highly recommend using a small electric screwdriver or hand drill to speed up the assembly process. The heart of this actuator is a 5010 brushless DC motor. These are commonly used on large drones, and you can easily find them on Temu or AliExpress for under $15 AUD. For the amount of power they produce, they're an incredible value. Next, we have the motor mount, followed by the helical ring gear that forms the outer gear of the planetary gearbox. The gearbox has been designed with a precise 4-to-1 reduction ratio. We also have the planet gears, the planet carrier, the bearing carrier, and finally the end cap that seals everything together. All of the bearings, fasteners, and hardware are listed in the description below. Let's begin the assembly. The first thing to do is position the motor so that the wires exit through the opening in the housing. This not only keeps the wiring organized, but also gives the rotor plenty of clearance to spin freely once everything is assembled. Using the 4 M3 by 10mm screws supplied with the motor, bolt the motor securely onto the motor mount. Since these screws are included with the motor, there's no need to purchase them separately. Next, mount the sun gear onto the motor shaft using 4 M3 by 12mm screws. And here's a quick tip. Don't use a power drill for this step. The rotor magnets are surprisingly strong, and if your screwdriver slips, those sharp rotor edges will remind you very quickly why hand tools exist. Trust me, your fingers will thank you. Once the sun gear is installed, place the center bearing carrier over the top. This holds a 10mm inner diameter, 22mm outer diameter, and 6mm thick bearing that supports the planet carrier. We'll leave that aside for now and move on to the planet gears. Each planet gear uses 4 bearings, measuring 4mm inner diameter, 10mm outer diameter, and 4mm thick. Simply press fit each bearing into the printed gear. The printed spacers fit between the bearings and the gear to keep everything perfectly aligned. Once each gear is assembled, bolt them into the planet carrier. Before moving on, make sure every gear spins smoothly, with almost no resistance. Now it's time to join everything together. Using 4 M4 by 40mm screws, bolt the motor mount to the helical ring gear. Pay attention to the orientation here.
The gear teeth should face away from the motor, leaving clearance inside for the heads of the planet carrier screws. For the printed threads, I actually recommend using a tight tolerance print rather than heat set inserts. Simply run the screw through the plastic to form its own threads. It's quicker, lighter, and works surprisingly well for this application. Before sealing the gearbox, rotate everything by hand to make sure the gears mesh correctly and spin freely. If anything feels tight, now is the time to fix it. Finally, press the large output bearing into the top of the planet carrier. This is a 45mm inner diameter, 58mm outer diameter, and 7mm thick bearing. Place the end cap on top and bolt everything together. And just like that, you now have a fully functional 4-to-1 brushless servo actuator ready for your robot.
Now, you might be wondering, if the final design uses a cycloidal gearbox anyway, why not just connect it directly to the motor? The reason is that planetary gearboxes are much better suited to handling the very high RPM of a BLDC motor. By reducing the speed by 4-to-1 first, they also multiply the available torque before it reaches the cycloidal stage. That means the cycloidal gearbox operates at a lower input speed, with less vibration, lower bearing loads, and better overall efficiency. Instead of asking one gearbox to do everything, each stage does what it does best. The planetary gearbox provides an efficient first reduction, while the cycloidal gearbox delivers the large final reduction needed for a robot joint. Together, they create a smoother, stronger, and more compact actuator with an overall 100-to-1 reduction, perfect for this DIY cobot project.
So where would a collaborative robot like this actually be used? Cobots are becoming increasingly common in factories and small businesses because they can safely work alongside people without needing large safety fences. You'll find them performing tasks like pick and place, machine tending, packaging, palletizing, quality inspection, screw driving, dispensing adhesives, and even light assembly work. The goal of this project isn't to compete with industrial robots worth tens of thousands of dollars. It's to create an affordable, open-source platform that anyone can build, modify, and learn from. Whether you're a student, a hobbyist, or an engineer, you'll be able to experiment with real servo-controlled robotics without the industrial price tag. Now I want to give a huge shout-out to Mission Machine for releasing his incredible 3-phase cycloidal gearbox as open source. His design made it much easier to customize the actuator and adapt the motor position for this robot. This actuator is only the first stage. Right now, it provides a 4-to-1 reduction. But the real magic happens when we attach a second stage cycloidal gearbox with a 25-to-1 reduction. Multiply those together, and we end up with an overall gear reduction of 100-to-1. That puts the actuator into the same ballpark as many industrial collaborative robot joints in terms of output torque, especially considering this entire project is built primarily from 3D printed parts. And yes, believe it or not, I actually asked ChatGPT to help select the motor for this project. If you'd like to build one of these yourself, you can download all of the CAD files using the link in the description below. If you enjoyed the video, consider leaving a like and subscribing, because this is only the beginning of the complete DIY collaborative robot build. Thanks for watching, and until next time, let's rotate.